Okay. If yesterday you were like confused on the homework, I'm sorry about that because we didn't get to go over some of the things I wanted to go over in class with the combinations and things. But that's why we're doing a homework review so that you guys can understand these concepts. So, yeah, let's get started. So the first question on the homework was evaluate 6 factorial plus 5 factorial plus 4 factorial divided by 3 factorial plus 2 factorial. So I guess if someone like wants to explain, they can.
Yeah, may I stop? Vika, do you want to? You can just go for it.
Yeah.
One second.
Okay.
Okay, so for this first, I put 4 factorial outside, and then in the bracket, I put 30 plus 5 plus 1. And then I divided that by 2 factorial outside the parentheses. Plus, okay, so that'd be 3 plus 1. Next, I wanted to cancel out already. So on the bottom, we have 2 factorial. So then on the top, we'd have 12. And then since now on the bottom, we only have that 4, we can cancel out that 4 with the 12, so it becomes a 3. Now inside there, it becomes a 36. Then we do 3 times 36, or 12 times 9, and it becomes 108.
That's amazing. Great job. That's exactly right.
Okay. Number 2, how many ways can the letters in the word combo be arranged? Does anybody want to go through that? Does anybody want to do number 2?
Can I?
Yeah, Ian? Is that how
Yeah.
you pronounce it? Yeah, go for it.
So because it's 5 letters, it's 5 factorial. And then because there's 2 O's, you have to divide it by 2 factorial. And so 5 factorial divided by 2 factorial is 3 times 4 times 5, which is 60.
Yeah, that's excellent. Good job. So it looks like you guys remember how to arrange words and to deal with repetition. So that's a really nice job. So number 3, today you need to clean your room, do the laundry, go to tennis practice, and complete your homework. It actually sounds like a pretty good outlook of what you usually do on a day-to-day basis. You clean your room or do the laundry directly after tennis practice, and you don't want to do your homework last. How many ways can you schedule your tasks? Yeah, this is like exactly a description of my life. Yeah. Does anybody want to do this? You need a little help on this one.
Yeah, I
That's
can
fine.
understand that. If you guys want, I can demonstrate this problem. Okay, I'll do it. Okay, so let's just, for the sake of like saving space, I'm just gonna call cleaning your room A, and then doing the laundry B, and going to tennis C, and homework D, just because I'm not gonna write all those out.
So now that we've reconceptualized the problem, does anybody want to try? Because we've actually done these kinds of problems before. Does anybody want to just go for this now that we've reconceptualized it? Okay, looks like we're still getting different kinds of answers. We've got a 12, we've got a 4. Amy, just continue with your explanation.
Okay, so I'm going to make 4 blanks representing when these events are happening after each other. So first of all, we don't want to do our homework last. So that means D has, actually, let's not even focus on D first. First, let's focus on C, which is going to tennis. Reason we're going to be focusing on C is because the question gives a restriction. You don't want to clean your room or do the laundry directly after tennis practice. And what that means is that you can't have C and A like this. You can't have A right after C, and you also can't have B right after C.
One
Yeah.
of the teachers, what? Wait, who said the answer was 6? Actually, it's fine. We can just continue. It doesn't matter.
Okay, so C can go into several positions. We can't, okay, I'm sorry, I'm checking for the chat. Okay, so we can consider different cases. So first, we can have C be in the leftmost position. And if C is in the leftmost position, then that means that A and B, this means that A and B can either be here, or here, oh shoot, or here, in any order. So this could be, and the reason being that we don't want D in the last position. So we could either have CDAB or CADB. However, the A and B can also be flipped around. So it could be CDBA and CBDA. So for this case, we have 4 possibilities. And yeah, the answer, yeah.
CADB, because I thought that was restricted.
Yeah, it's,
Oh, shoot,
yeah,
you're right.
yeah,
Sorry.
yeah. I got
Sorry.
2 as well. I was
I
kind of
didn't mean to do it.
confused
Yeah,
because I
okay,
think it's
sorry
only
about that.
I think it's only CDAB, Amy.
Yes.
Because-
Yeah, it would
wait,
be
what's
just CDAB. Sorry, I kind of forgot about that.
I have a
It's fine.
question.
Yeah.
Couldn't
Yeah.
we also do like C's in the third spot and we do A and B in the first and second?
Yeah, that's
We're,
another one.
we're
That,
approaching those in cases. So our
Yeah.
first case would be C is in the leftmost position. We're gonna go for C is in the second position next,
yeah,
and then the third position. We're gonna do so. Then we get the cases in an efficient manner. You
yeah.
understand that?
So this is
Yeah.
just the first case. The next case is if C is in this position. In this case, the only positions that A and B could go in would be the first and last positions, because A and B can't be directly after C. So for this, we would also have 2 possibilities because A and B can also be flipped around. And then the third case is C in the third position. In this case, D just can't be back here. So for this case here, let me erase this. For this case, D can be here with A and B flipping around here. Or D can be here.
Wait,
Or
Amy.
wait, what? I'm sorry.
But that's
Correct me if I'm no. Correct me if
Sorry.
I'm wrong.
I keep forgetting. I
Yeah.
told you my brain's not working today.
Yeah. I was thinking that this case had no possible.
Yeah, that would
outcome.
have no possibilities.
Because you can't have D in the last slot, and you can't have A. And if D can't be in the last slot, it has to be in one of the first 2 slots, right?
Yeah. Okay. I'm
And you
sorry.
Yeah, that means you have to have A or B in the last slot, so that would
Mhm.
fit. So C
Alright.
C in the third slot does have
Yeah.
0 options.
Yeah.
And
This
the
does
only
not have anything. However, the last case has 6 possibilities because A, B, C, and D can be in any order over here. So that would have 6. So then the total would be 2 plus 2 plus 6, which is 10.
good job, guys. Yeah, that's exactly it. Does anybody have questions? Are there any questions? If not, we can just move on to the 4th. Can anybody do I thought it was 4 because Miss Shani said 4 was correct. Okay. So the answer actually isn't 4. Wait, are you talking about number 3? Elvika, are you talking about number 3? Did Shani
Yeah.
say number 4? Yeah,
I think
that's not. I
Shani
don't
made
think
a
that's.
mistake,
I think
probably.
Shani. Yeah, Shani probably most likely made a mistake. It's definitely not 4. I don't think she considered maybe the last one of the cases. Wait, she said 4 and 6 was correct.
Yeah, she
Hmm.
said.
Um, well, that's. mm, I don't think she's right. I don't think she's right. I'm pretty sure it's 10.
Yeah.
Okay.
Yeah, it's fine. Yeah. So as long as you understand how we did it and how we got to this answer, it's fine. Does anybody want to do number 4? Yeah, Sahil, go ahead.
Okay, I think I got 8.
Okay.
Okay.
This was actually a really cool question, in my opinion. It's a question it's a very nice question. So for this question, you don't want to use casework.
I meant, yeah.
You don't want to use casework for this question because it would just be too cumbersome.
Like there's a lot of
So
triangles. Let's just say that.
yeah, it's a lot of triangles. Yeah. So basically, what we're gonna do here is we're gonna be a little smarter, right? We're gonna use some big brain tactics. So think about it. How many vertices does a tri? Actually, Sahil, you said you were gonna do it. Sorry, I don't know why I'm explaining anything. Sahil, do you want to just explain to everyone how you got your answer?
So I did.
I don't know if I can hear you. Amy, do you hear anything? Okay. Well, it's fine. I think you got the correct answer. So this is how we do it. Think about it this way, guys. So a triangle has 3 vertices. Everybody knows that, right? I would hope. Oh, wait. Are you there? Because yeah, we couldn't hear you. We couldn't hear you, Sahil. Yeah, yeah, that's because right. So a triangle has 3 vertices, and we have 9 total vertices here. Probably shouldn't draw on this, but so basically that'd be 9C3. Can someone in the chat put what 9 choose 3 is? A4, exactly. And just as a refresher, 9 times 8 times 7 divided by 3 times 2, and then we cross out the 3 here, and we get 84. So yeah, 9 choose 3 is 84. But wait, there's something that we have to consider. If the 3 points were chosen like this, then that's not a triangle. It's just consecutive points. So if those 3 vertices were like this, we wouldn't have a triangle. And Amy's just gonna draw out all the possible ways that we wouldn't have a triangle. And it
Yeah.
should sum in total. So look, 1, 2, and then 3, and 4, 5, 6, and then the diagonals. You have to consider the diagonals. So in total, there are combinations in which we cannot have a triangle. So our total answer is 84 minus 8 or 76. Does anybody have any questions? Are there any questions? Hello, guys. No questions?
No questions.
All right, cool. Nice. If everybody understood that, we can just move on to number 5. Does anybody want to do number 5? Can I do 5? Tanisha, go ahead.
So what I did was I did 9 choose 3 times 8 choose 3, and then you get 84 times 56, which is 4,704.
Yeah, that's probably, wait, let's look at this. Yep. And Tanisha, is this combinations or permutations?
Uh,
Wait, remember, permutations is where order matters, and combinations is where order doesn't matter.
Permutations?
Okay, so this is actually combinations because we don't really care about the order because it's a council. It's not like anybody here has a role, a specific role. Since everybody has the same role, it doesn't matter the group of people we select because we don't really order that group of people in any specific hierarchical combination or way. So it would be combination because the order doesn't matter here. Do you understand that?
Yes.
Yeah, that's good. You can continue. Wait, I think you already said it, right? Yeah, that's it. It's pretty much a straightforward problem. 9 boys, 9 choose 3. 8 girls, 8 choose 3, and you multiply that. So that's a great job, Tanisha. Good job. Good job, everybody. Looks like you guys all understood the homework and we were able to do it fairly easy. I think the only trouble on was number 3, but we were able to do that. So good job. I was sharing the second problem. Amy, do you want to do the second problem one more time?
Okay, second problem.
Because it's pretty easy.
All right. Just as a refresher, the way we get the number of permutations in a word is to take the factorial of the number of letters in the word. So the word combo has 5 letters in it. So we would do 5 factorial. However, since there's actually repeated letters, there's 2 O's. And whenever we have a certain number of repeated letters, we have to divide by the factorial of those repeated letters. So we would just do 5 factorial divided by 2 factorial, which is 120 divided by 2, which is 60.
Yeah. Yeah, so it's pretty simple. Okay.
Okay.
Does everybody understand?
Okay. All right. All right, let's move on to the actual lesson. So today we're going to be learning about a bunch of different types of problems. We're going to be learning about handshake problems or team problems, table and bracelet problems, complementary counting, sticks and stones strategy, and strategies for line path problems. Basically, today's lesson doesn't actually have a lot of new content. Instead, we're just focusing on how to apply what we learned about permutations and combinations to different types of problems. So first
Yeah.
up, handshake and team problems. Yeah. Okay. So it goes something like this. There's like 10 people in a room, and each person is going to shake hands with every other person. And we basically just want to find how many handshakes will occur. So in order to do this, we can think about the problem like this. The first person, which is the leftmost person here, is going to shake hands with everyone except himself or herself. This means that he or she shook hands with the 9 other people, right? So let's just write that down, 9. Then the second person in line, which is like this person here, will shake hands with everyone except the first person and himself. So this person will shake hands with this person, this person, this person, this person, this person, all the way. So this means that the second person shook hands with 8 other people. And this pattern just basically continues until the very end, when the last person doesn't have anyone else to shake hands with because everyone else has already shook hands with him. So that means the total number of handshakes, we would have to add up all of these values. So it would be 9 plus 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1, which is 45 handshakes for 10 people in a room. Yeah, I didn't actually draw this. Just took it off of, for some reason, Wikipedia had a picture of a stick figure. So I just took that. Yeah, okay. So does everyone understand how this works? So like the first person, if there's 10 people in the room, the first person shakes hands with 9 people, then it goes all the way down. Okay, nice. All right. So if you're a similar type of problem comes up when you have a bunch of teams in a tournament. So you guys can try this. In a certain league, every team plays against every other team exactly once in a tournament, and the teams with the most wins is the champion. If the league has 16 teams, how many total games will be played?
Okay, so when you add from 1 through 9, like Amy said, like 1 through 9, that just I don't know if everybody knows this formula, but to add like to a certain amount of numbers, it's 9 times 2 divided by 2. So like the explanation that I put in the chat, it basically equates to that one. So everything's simplified because 10 people.
Yeah, Shreya,
I'm
you're close. Just notice that in the previous problem, we had 10 people in the room, but we started adding from 9. So for this problem, we have 16 teams, but the first team would actually have to play 15 games, not 16.
also just you kind of use the logic that I put in the chat. You're probably gonna get the answer pretty easily. Think about it. So I'm just gonna say one thing really quickly. How many? Okay, it looks like we already have an answer. I was just gonna say, how many teams does each team play? So if you just think about it like that, how many teams does every single team play? 15, right? So it'd be 16 times 15. But wait, we would be counting twice as many games then, because by multiplying 16 and 15, a team that played, if we said team A played team B, we would also be counting team B playing team A, but that's the exact same game. So that one single game is being counted twice. So we would divide that by 2. So 16 times 15 divided by 2 is just 8 times 15, which is 120. So, yeah, pretty straightforward. Does everybody understand? Also, once you get more proficient at this, you don't want to add it. You don't want to
Yeah,
add up.
don't add them out. I'll introduce
Don't-
a little shortcut in a moment.
Yes, okay, everybody
Yeah.
seems to understand.
Also, let me just recap on the 2 different strategies me and Sai showed you. Basically, the strategy I showed you is that for each the first team would play 15 games against all the other teams, but the second team would play 14 games because the second team already played the first team. That's one strategy. Sai's strategy is that every team will play 15 games, but we have to every team, so we have 16 teams, will play 15 games. So we do 16 times 15. However, if we just do it that way, we count each game twice because we have one team play another team, but that same team plays the other team. Even though that's technically one game, we counted it twice. So we have to divide by 2. That's why we did 16 times 15 divided by 2. Or 15 times 16 divided by 2. And this is a little formula. The number of handshakes for games that will occur or be played in a room or tournament. Okay, that's confusing. Okay, the number of handshakes that will occur in a room of n people is n times n minus 1 divided by 2. Or if the same thing applies for games. So let's do another example. If you
Another thing, really quickly, it's probably best that you guys understand this. I didn't memorize any for this. You probably shouldn't even memorize this. It's just here for like to generalize this relationship, but you probably shouldn't memorize this.
Yeah, make sure you actually understand how it works.
We did 15, 16. So how is n minus?
There were 16 teams. Oh, Advika, it could be really it's like 16 times 15 over 2. Either way, it's the same. There were 16 teams times 16 minus 1 over 2.
Yes. So the reason why it's 15 is because you don't play yourself. So each team plays 15 other games. So let's say I'm playing, okay, I'm gonna kind of simplify this. Let's say I'm playing a game versus Amy and like Bob, okay? Right? So, and I play a game with every single person. So I don't play a game with myself. I play a game with Amy and Bob, right? So even though there's three people, I play with two other people. And same thing for Amy and Bob. Amy plays against me and Bob. So each of us play two other people. So if each of us play two other people and there are three of us, then we each so then that would give us what, three times two, right? But the issue here is if I play against Amy and Amy plays against me, that kind of counts. We're kind of counting both of those as two separate games, but they're not. They're just one game. So we divide by two. So we get 6 divided by 2 or 3. You understand? So just remember that you don't. Yeah, that's good. So just remember that you don't play yourself. You don't play yourself. You play every other person but yourself, right? So that's why you have to have that n minus one, and then you divide by 2 because you're counting duplicates. You're saying you're saying that one game, you're counting one game as two games because yeah, because when you multiply like that, what you're doing is saying if each team plays that other team, then that that interaction between that team and another team is one, and then when you go to that rotation and do the exact same thing, then it's another game, and it's just it gets tangled up, and at the end of the day, you have twice as many games. It's a little harder to explain, but it's not that hard to really understand why you divide by two.
Okay, I want you guys to just do a quick example. If we have 15 teams in a tournament where each team plays every other team once, how many games will be played?
Yeah, so Vishwa, you're right. It's and Vishwa and Vika and Tanisha and Treyon. Yeah, you guys are all right. It's 105.
Yep.
Good job, guys. We'll move on.
Okay.
Oh yes.
All right. It's important that you know how to do these team problems because they come up a bit in like tests. So yeah. Okay, now we're gonna do something a little bit related, but also a little bit different. Our table and bracelet problems. And I'm gonna so you can do this because yeah.
All right. Yes. So I actually do like these problems. So because they're a little different. Okay. Alex, Barry, Celia, Dwayne, and Esther need to pick seats around a round table with 5 seats. How many distinct seating arrangements are possible? Now, intuitively, you might say 5 factorial, right? You just might say 5 factorial, but you have to think about this. It's not 5 factorial. Why is it not 5 factorial?
Like what makes sitting around a circular table different from arranging things in a line?
Because if you go forward, it's the same thing as going backwards.
Exactly.
Rotations in circular tables. So in a linear table, there's an end and there's the beginning, but there is no end and beginning in a circular table, and you can rotate it. So we would have to divide by 5 instead. So we divide 5 factorial by 5 to get 24. I hope that's right. Divide by 5, yeah, that's what, okay, that's nice. Yeah, so we do divide by 5. I thought maybe I calculated that wrong.
Yeah.
120 divided by 5. Good, yeah, 24. So right, so we divide by 5 because we rotate the table. So actually that might sound a little confusing, but look at the illustration Amy kind of did for us. So A, D, B, C, E, right? Now the seating arrangement on the right might look like a different seating arrangement, right? It's like at first glance, but all we're doing is just rotating everybody to the right. So we have the exact same seating arrangement, except it's rotated to the right. So think about it like this. How many total ways can we arrange that same seating arrangement with the different like orientations? And that would just be 5, right? Because there's 5 seats in the table. So if we move it right one more time, we would have A in the bottom right, and then one more time bottom left, and then you know and then one more at where C is right now, and then yeah. So basically, there's 5 ways we can do that. So we have to just divide by 5 to get the distinct arrangements.
Yeah, we got 120 by first doing the normal, 5 factorial, but then we had to divide by 5 because each of the 5 rotations is actually one arrangement. So we have to divide by
Yeah,
5.
yeah, each 5 rotation is one arrangement. It's just a different orientation.
Okay.
We're trying to find the distinct orientation. Okay.
So then let me ask you guys a question. If we have 6 people sitting around a table and we want to find, basically, every time you have like a table problem where like, oh, there's a bunch of people sitting around the table, if it's just like a normal like table problem with no like weird constraints, then yeah, this would be the strategy you use.
Wait, isn't that just 4 factorial?
Yeah, that is also 4 factorial. You could just do n minus 1 factorial for n people.
Okay.
If you guys have if you have 6 people sitting around a table, what would you do?
Okay, well, it looks like we already have an answer.
Yeah.
That's exactly correct. 6 factorial divided by 6. 6 factorial ways to arrange the 6 people. We divide by 6 because because of rotation, which gives us the same arrangement in different orientations. So 120.
Yep.
Okay, everybody understands that. Good job, guys.
Oops, we just did that. Okay. All right, now we're gonna look at bracelets. Bracelets are pretty similar to tables because you're arranging things around a circular object. However, bracelets also have a catch.
They do have a
Yeah.
Yes, they
Basically, if you just do the normal thing we did with tables, we would get, if you're trying to arrange 5 different colored beads on a bracelet, you would first do 5 factorial divided by 5. We divide by 5 again because you can rotate. But then if I don't have a bracelet on me, okay, I have this USB cord, pretend this is a bracelet, okay? You can flip bracelets.
Yeah.
That's the problem.
Guys, you can flip I said basements. You can flip bracelets when you can't flip a table. I mean, you probably could flip a table, but you couldn't flip the people sitting at the table.
Yeah.
I mean, you probably could do that as well, but it's just not something we consider, right? Because it's very unlikely. But bracelets can be easily flipped, right? You just flip them. So since bracelets can be rotated and flipped, we also have to divide by 2 along with the 5 we divide to account for rotations. So in order to account for flipations probably isn't a word. To account for the flips, we divide by an additional 2.
Yes, Shreyan, that's right. Okay.
So 120 ways, divide by 5 for the rotations and divide by 2 for the flips.
Mm-hmm. Yeah. And just to recap everything, for tables, to find the number of possible seating arrangements for a table, we do n factorial divided by n, which is just n minus 1 factorial. This is because tables can be rotated. For bracelets, in addition to that, we have to divide by 2. Okay, I see someone is a little bit confused, so I'll re-explain again. For table, wait, are you confused about the tables or the bracelets? Or both?
Maybe both. Okay, bracelets.
Okay.
Well, bracelets are the exact same scenario as tables, right? Think about it like this. You cannot flip a table. Not realistically. Like,
well, think about it like this. Basically, if you flip something, that gives a new arrangement. But in real life, however, the arrangement of beads on a bracelet is going to be the same regardless of if you flip it or rotate the beads around. So, however, in a table, you can't really flip the table upside down and like expect it to like still be like normal.
Yeah,
so,
that's a little thing, but yeah, basically the way I learned it is that like you just can't consider the flip of the table because it just doesn't. You just can't account for that. It doesn't really make sense to do that. But we flip bracelets around, right? It's very common. So when bracelets can be flipped, tables cannot be flipped. It's as simple as that. So when you flip a bracelet, you're just getting the same arrangement, except in this different kind of, because we're flipping it.
Tanisha, yeah, you would have to divide by 2 to, but
And then
remember that you'd still have to divide by 5 because bracelets can also be rotated.
you rotate it. So you have to just, okay, think about it like this. The only difference between bracelets and tables is that bracelets can be flipped. But there's one more thing, like the beads on our bracelet could be the same color, but that's not something we're gonna get into right now. But, well, are we?
Yeah, 5 factorial divided by 5 divided by 2.
Yeah, but the biggest thing between bracelets and tables is that bracelets can be flipped and tables cannot be flipped. So we have to divide by that additional 2 to account for the flips.
I question, if there's a circle table in the pattern A, B, C, D, E, would A, E, C, D, B be different? Hold on, I'm assuming that's a flip, but I'm gonna have to check. One moment.
Wait, is that a table? You don't count flips and tables are different. They're different. They're counted as different things. 'Cause
Yeah,
you don't,
so those 2 arrangements would be different.
yeah, you can't flip a table.
So Hill, yeah, you can do 5 factorial divided by 10.
Yeah. Yeah, but yeah. If you can just account for that division like totally, because 5 and 2, but you can do it however you want. You just have to make sure you get that flip accounted for.
Yeah. Also, let's do just one more problem with bracelets. If you have 6 beads on a bracelet, how many distinct arrangements of those beads are possible?
Yep, 6 factorial, but wait. Not exactly,
Mm.
not exactly 6 factorial. You're kind of close, but you missed it.
Yeah, it looks like most of you guys got it. So it would be 6 factorial first, and then we divide by 6 for the rotations, and then we divide by 2 for the flips. So that would give us 60.
I have a challenge. Do you guys think you can find out total bead arrangements if we have 6 beads, but 3 are one color and 3 are different colors? So 3 are red, 3 are blue. So how do we do that?
And if you're confused, think back to our letter arranging problems. Wait, Sai. Did you say 3 red, 3 blue?
3 red, 3 blue.
Okay.
Looks like we're getting some different answers. Let's see. Okay, so we are getting a couple of different answers. Wait, do we address that the repetition of bead
No,
color?
not
We
really.
don't address it. All right. Well, I think I'll just save it for the end then, because it's actually it's actually not as hard as you might think. We can just move on for now, but on the Jamboard I can just address that.
Okay.
You guys shall find out later. Yeah, you have to be attentive for the rest of the class. Wait.
Oh wait, let
Moving
me
on
give
to-
you the link. Oops. Whoops. I'm trying to find the chat. There we go. Okay, there's a Jamboard for you guys. We're on slide 2. All right, slide 2. In the Big N, which is a middle school football conference that I'm pretty sure doesn't exist, each team plays anything. I don't know. I got it from the AMC thing. Each team plays every other team exactly once. If a total of 24 games were played during the 2012 season, how many teams were members of the Big N conference? And by the way, anyone can just write on the board if you have an answer. Let me just say something. This question is actually working a little bit backwards. Previously, we asked you how many games are played with N teams, but this question is asking how many teams are there with a number of games. So you do have to work a little bit backwards. Oops. Yeah, it is 7. How'd you get that answer?
So for 7, so I remember we did n times n minus 1 divided by 2. So my first step was I multiplied 21 by 2. Then next I kind of just went to 7 times 6 immediately, and I checked. So it became 7 times 3 is equal to 7 times 3 is equal to 21. And then I was about to say 6, but then I remembered it was n minus 1. So that's how I went to 7.
Yeah. Yeah, that's basically it. Just to recap, this is how many games are played, n times n minus 1 over 2. That should equal to 21. So all you're doing is basically solving this equation. And if you decide to multiply n out, you will get a quadratic. And it might just be easier for you to just use a little bit of common sense and think, oh, what number times what number, close number, equals 42. And then you would come at 7, just like Advika did. So good job. And I know some people were thinking that maybe 21 was the number of teams, because if you did 21 times 20 over 2, you would get 210. However, be careful about the question, because it says that there were 21 games played and they're asking for how many teams. So, yeah. Okay. Are there questions? If not, I'm going to move on. All right, Sai, if you would like to do, or actually, we can you guys work on it for a little while, and Sai, you can do this problem.
Explain.
Okay. I know you guys are probably still solving it, but if you have any thoughts on like what you're doing or anything you're confused about, you can definitely just say it out loud. Okay, Shran, you have an idea, and I see Tanisha raised your hand. Shran, could you, if you want to, you can share your idea.
Okay, so I'm not completely done, but so if you look at the problem, what I'm just gonna do is that so each twin would I think would shake hands. Oh wait, as if it wasn't need to double everything with 48 people, right?
Mm-hmm. Where did you get 48? Let me just ask.
So he will not shake hands with himself and his or her sibling.
Yeah.
So for the twins part, right?
Mhm.
So they will shake hands with wait, why did I put 48? That okay, never mind. So there'd be 16 twins. I don't know what am I doing right now. I'm not. So 16 twins, and there would be 9 triplets. So actually it should be 25. So 25 handshakes per 9 twins, 25 times 9 is 225. Now for the triplets, one. Okay, I keep on realizing I'm doing need to change something. So let me just make sure I'm doing the twin math correctly. So actually there are 18 twins. So I need to multiply 25 times 18. So 25 times 18 is
Maybe you don't have to multiply it out. Maybe you just keep it on your paper.
yeah, I'll just keep it on my paper. I'll not multiply.
Okay.
Yes. But that's what I'm doing. I'm just finding the amount of handshakes per person, and then I'm just gonna add them with the total amount of handshakes for all twins and the total amount of handshakes for all the triplets.
Yeah, that's on the right track. That's how I would do it. Someone wrote 279. That's not the right answer, but I mean, I guess, yeah. Both
Okay.
sexes.
It looks like you guys are getting various answers. And Tanisha, did you raise your hand?
Could you explain, if you have time, the other one about the football thing?
Wait, the football?
Yeah, the football thing on slide 2.
Football. Wait.
The
Slide.
previous question.
Oh, my bad. Okay.
Yeah, that's what I meant.
Actually, Amy, do you think I could explain it? Yeah, actually, I'll just explain it after this problem, okay?
Okay.
So, 9 sets of twins, right? So that's a total of 18 people. I'm just gonna erase everything. Oh, sorry, guys. Yeah, I'm ruining your numbers.
I mean, you guys are on the right track. You're doing it in the, I believe you guys are doing it in the correct approach. I just haven't seen the correct answer yet, unfortunately.
9 sets of twins, okay, and each set is 2 people, right? So 18 people. 6 sets of triplets, so that's another what, 18 people. Now each twin should count with all the twins except his or her siblings. So you can't shake hands with yourself and you can't shake hands with your sibling, right? So each twin shook hands with 16 other people. So we have to divide by 2 here in order to get rid of all the duplications. So you get 144 for this.
Ooh, Advika, you're very, very close, except you forgot one thing.
And then another thing is, except his or with half the triplets. So half the triplets is 9 people. So all 18 shake hands with 9 people, but then we have to divide it by 2. And we get 81 here. Now for the triplets. Oh, sorry, my battery is running low. All right, I had to do something really quickly. Okay, so yeah, I'm gonna continue on. It says half the triplets with half the triplets. Yeah. Oh, yeah. Each triplet shook hands with all the triplets. Okay, so well, except his or her siblings. So can't shake hands with yourself, and your 2 other. So each one shook hands people. Divide by 2. Get 135. And then with half the twins, so all 18 should cancel with half the twins. Divide by 2 to get rid of the duplication. Does everybody understand up until this point though? So 882 is not the answer, but I just want to make sure that everybody understands up until this point. Okay. Well, if there are no questions, we get 81 here. So once we add everything up, we get 162, which is 81 plus 81. It's 144 plus 135.
The reason why we divided by 2 is because the way we're counting it, it would make it so that if person A is shaking hands with person B, but person that at the same time person B is shaking hands with person A, right? That's only one handshake. But the way we're counting it, it makes it seem like person A shaking hands with person B is different from person B shaking hands with person A. So we have to divide by 2.
Yeah.
Yeah, the numbers count both of it. So you would have to, so 882 is very close. You just have to divide by 2 to get 441.
Yeah. 82. Yeah. You just forgot to divide by 2. But yeah, you're pretty close. A nice attempt.
Does everyone understand that?
How did you get 135 and 81 again? Like,
Okay. Yeah, for those, you understand. Okay, for that one, we have here's my laser pointer. We have 18 triplets, right? And wait a second. Oh, and each of the triplets is shaking hands with half of the twins. And since there's 18 twins, that means half of the twins would be 9. So we do 18 times 9.
mhm.
But then we do have to divide by 2 because, as you remember, the way we're counting, each person shaking hands with another person is counted twice.
Yeah.
So we have to divide by 2.
Okay.
And for this last one here, I kind of forgot what side I did here. Sorry.
What?
For the 135 part.
Okay, well, so the 135 part, I have, and remember, it's the triplets now. So the triplets, there are 18 triplets, and they can't shake hands with the other twins or their siblings. They have 2 siblings, so they can only shake hands with 15 other people in their triplet group. So 15 people, right? And there are 18 total twins. So it'd be 18 times 15, but then we have to divide by 2 to get rid of the duplication, and we get 135. Now, why did you do 18 times 16 again? Okay. So for 18 times 16, you can't shake hands with yourself or your twin. So it's only 16. So like for the triplet and twin part, would it be okay if I did 16 plus 9 times 18? Yeah. So Amy can answer that. Anyway, so then we have to divide by 2 to get rid of the duplication, right? Because well, you guys, I think we explained why this duplication is there, like pretty in depth. So I'm
Yeah, I
assuming
got the duplication, but so is the first part the twin part and like the second part the triplet part? Is that what you're saying?
yeah, you guys have to read the
Oh,
questions.
yeah.
I did this one first. This part is that first part, and then I did this part next. So that part is this part, and you add everything together.
Okay.
Okay. All right. Yeah, we can do this question and then we might need to move on because
I think someone asked you slide number 2 again if we had time.
we might not have enough time. We can come back to that later because
Okay.
right now we have a lot to go through. Okay, so for this question, Mary has 1 red bead, 1 green bead, 1 yellow bead, and 2 blue beads. She wants to make a bracelet with these beads. How many bead arrangements can she make? whoever's writing on the slide, you're on the right track. Just do note that there are these two identical blue beads. Advika, I think I think you're right. So basically, when you first approach this problem, you just do this in the same way that you normally solve these bracelet problems. You do 5 factorial, and then you divide by 5, and then you divide by 2. However, because you have these two identical blue beads, you have to divide by 2 a second time in order to compensate for these. Because you remember when we're doing the arranging words, whenever we have 2 repeating letters, we divide by 2 factorial. We do the same thing here. So after we do 5 factorial divide by 10, we have to divide by 2 again. And that gives us our answer of 6. Any questions? If not, we're going to be heading back to the slides because, yeah. Okay, that's good. All right. Our next topic, hopefully we can go through this one a little bit quickly. I think you guys sort of already know what this is. We're going to be learning about complementary counting. What is complementary counting? Sometimes when you're solving problems, it's actually easier to find the opposite of what the question asks you than to find what you actually need to solve for. And this is where complementary counting is useful because sometimes it's a good idea to actually find the opposite and then use that to find the actual answer. So let's look at an example. In 5 flips of a coin, how many ways can at least one head be flipped? And I mean, okay, first of all, you guys try to identify what would the opposite of this question, like what would be the opposite of what this question is looking for?
Would it be like in 5 flips of a coin, in how many ways can at least one tails be flipped? Or at most one head can be flipped?
Close. How about no heads? It's asking for, think about it like this. It's asking for the number of, the question is basically talking about the number of heads. And this question wants at least one head be flipped. This means that the question wants 1 head or 2 heads or 3 heads or 4 heads or 5 heads or 6 heads or however many more heads you can have. Oh wait, it's 5 flips. So it'd be 1, 2, 3, 4, or 5 heads. So the opposite of this would actually be 0 heads. So then, and compare, like, think about it. Think about how easy it is to find the number of ways to flip 0 heads compared with the number of ways to flip 1, 2, 3, 4, and 5 heads. Like there's only one way to flip 0 heads. So you might as well just find the number of ways to flip 0 heads. And so how many ways are there to flip 0 heads? You guys seem to be putting in probabilities, but I think that you guys understand. There's only one way to flip 0 heads. So in total, there are 2 times 2 times 2 times 2 times 2, which equals 32 total ways to flip 5 coins in any way. Why not 5? Because there are 5 flips. True, there are 5 flips. However, each flip can have 2 outcomes, heads or tails. If you get, here's the thing. Why not 5? Because there's 5 flips instead of 0. The opposite of the question would be 0 because if you flipped 5 heads in a row, that would actually satisfy the question. It's asking for at least 1 head be flipped, which means that if you flip 1 head, 2 heads, 3 heads, 4 heads, or 5 heads, that would satisfy the question. However, if you flip 0 heads, this does not satisfy the question. Oh, okay, sorry. If there's only one way to get 0 heads, because the only way that could happen is to get 5 tails. And since all these tails are identical, it's just 1. So since we know the total number of ways to flip 5 coins, which is 32, and we also know how many ways to flip 0 heads, which is 1, then what we can do is we can subtract the total number of ways from the opposite number of ways to get the answer. So there are actually 31 ways to flip at least 1 head. So does everyone understand that? You do the total minus the opposite to get the answer. Okay. That's
So,
good.
move on. It's fine. It happens sometimes to accidentally type in all caps.
Yeah, there's only one way to get 0.
Yeah.
Okay. Oh, we already did it. So yeah.
Yeah.
So you can do this slide.
So why would we use complementary counting? So if we use counting, you have to find the way 1 through 4 heads and 5 heads, and then add all of those up, and that's just inefficient. So instead, by being able to find the total amount of ways that we just flip 0 heads, and then subtracting that from 1, we get the correct answer in a really easy way. So it just takes a few steps compared to like the numerous steps we would have to take if we didn't use complementary.
Okay. All right.
So now you get.
Yeah. So you can still do this slide.
So Jasmine rolls 3 dice, then she adds up the numbers on the top 4 faces of the die. How many ways can she roll a sum greater than 4? This is, yeah, you would just use complementary counting again here as well. Okay. $108, nope, not quite.
Okay. Try to identify what's the opposite of this question. So the opposite of rolling sum greater than 4 would be yes, rolling less than or equal to 4.
Exactly.
Yeah.
What's the least sum that we can get? Everybody should know this. What is the least sum we can get when we roll 3 dice? The least 1 plus 1 plus 1, or 3, right? So we can either get a 3 or a 4, and there's only one way for us to get a 3, right? The only way we get a 3 is when we roll 1 plus 1 plus 1, and that only ever happens once, in one possible way or situation. How do we roll a 4? Exactly, there's 4 ways, because 2, 1, and 1, and 2, 1, and 1 happens in 3 different ways, because any of those 3 dice can be the 2. So therefore, we have 3 ways to roll a 4 and 1 way to roll a 3. So that happens in 4 ways. How many total ways can we roll 3 dice? Well, 6 times 6 times 6, right? So 216 ways. So using complementary counting, we get 216 minus 4, or 212 ways. Think about the alternative to this. It would be so incredibly tedious if we didn't use case rule. We'd have to count total ways to get a sum of 5, then a sum of 6, then a sum of 7, then a sum of 8, then a sum of 9, then a sum of 10, then a sum of 11, then a sum of 12, then a sum of 13, and we'd probably we probably would get the wrong answer, even if you didn't use complementary counting. So yeah, complementary counting really helps. And wait, why are there 216 ways? Think about it. So there's 6 ways I can get any number on the first dice, right? Because there were six total numbers on the dice. So 6 cubed, we're 216. Yeah, everything relates back to SCP with counting and probability. You understand? Yeah, okay, cool. All right, guys.
6 cube.
Well, not 3 cube, it's 6 cube.
Okay. All right.
All right.
We have break
Well,
time.
we have a 5 minute break. Yeah, so that's actually right at the hour as well. Almost hour. Wait, why don't we do 6 times 3 FCP said times 8 times B? Okay. It's because we have 3 different events. So each event has 6 possibilities. We're considering 3 events. They're not 2 events. So the first event has 6 possibilities. The second event has 6 possibilities, and the third event has 6 possibilities. So we get 216. I guess we actually have a lot more content.
Yeah.
Our other breaks were just located near the end
Our
of
other
the
breaks were actually a little bit overdue.
yeah. Yeah. Our other breaks were way overdue. But this break is more aligned, right? So yeah, we still have a lot more content. We still have like 30 more slides
Yeah.
around. We still have what?
And
Well, we
besides,
still
like,
have like
there's still a lot of like new cool stuff coming up. Like,
yeah, there's still lots of
Yeah.
stuff. We still I don't even think we're gonna have time to finish, to be honest with you.
that's kind of sad though, because there's like the line problems. Like, the numbering strategy side.
Yeah.
Yeah, that's
Yeah.
actually fun thing.
Yeah, like
It's a pretty
the
cool
grade,
strategy.
yeah, the weird grids. Yeah, I love the weird grids. I love the weird grids.
Yeah.
So guys, and I know you guys are gonna be really sad to not be able to see Amy's question slide, but we'll do everything in our power to get to Amy's question slide. Maybe she used a different pattern this time. So all
Dude,
right.
so I there was that like one time we were at like I think it was like chapter state on that target round at like for
Oh.
math counts. There was that
Huh?
line problem.
Oh yeah.
That
Oh,
was
yeah.
before I knew the numbering strategy. So I was literally just making cases with the like n choose m strategy.
Wow.
Like I was just
You know
marking
the
points.
grade problems.
Oh
You know the
yeah.
grid strategy is so fun. It's
Yeah.
so fun. The grids are probably
They're
the
fun
funnest
when
part.
they're fun once you like actually know like the strategy for them. But like
Yeah.
when I was doing it, I didn't know it. I was just like making a bunch of like cases and drawing all over the paper and like
All right. All
it was
right.
painful. But then I
Yeah.
still
Yeah.
happened to get the right answer.
Wow.
Yeah.
That's highly likely. Like, don't be inspired by Amy's story, guys. Don't do casework. Learn the strategies. All right. I'll see you guys in 2 minutes. Oh man. I'll see you guys in 2 minutes.
Hey guys, welcome back after a very refreshing 5-minute break.
Yeah, I learned something really interesting in my 5 minute break. I learned that Juneteenth will become an official holiday.
Yay.
I don't even know what Juneteenth means.
Juneteenth is the day that the Emancipation Proclamation, like the word that the slaves were free reached the actual slaves in the South.
Really?
Yeah,
Oh,
because there was a
well, yeah.
delay between like when Lincoln actually signed it and when it was like enacted, because the
Oh.
plantation owners, they didn't want their slaves finding out about it, so they tried to keep it a secret.
Yeah.
Juneteenth is like the
Mhm.
day when the slaves were like, oh my gosh, we're free. So or something like
Yeah.
that. I know.
It says that like it originated in Galveston. Wasn't Galveston like Houston? I think Houston, Galveston is like the same area.
Yeah, something like that.
Yeah,
Nice.
so I learned that they're making Juneteenth an official holiday. I didn't really know what
Yay.
Juneteenth. That's good.
Okay. So yeah, now we're going to be learning about the sticks and
Juneteenth is
stones.
June 19th, Cheyenne. It's June
Yeah.
19th.
There's a lot of things with teenth at the end, so yeah. Sticks
Yeah,
and
I don't know why it's called Juneteenth, but it's June 19th.
Yeah.
So it's
Okay.
19th.
I don't know.
All right, now we can go back on topic. It's just
Juneteenth. Wow. Okay.
13. Yeah,
Okay.
holidays.
Yeah. Okay. So
Go back.
we're gonna introduce you guys to this amazing strategy called the sticks and stones strategy. It's kind of hard to explain, so I'm actually gonna just walk you guys through an example and show you how we can use it. Cave people. Okay, so here's our example. Jordan wants to distribute 10 identical pieces of candy to his 4 friends. How many ways can he distribute the candy? And here's the thing, you guys might think, oh, we could just do like 10 choose 4. That actually won't work, because in this case, the candy is being distributed for the 4 friends. So it kind of like, I don't know, you can't do it with normal combinations. So I'm going to draw it out and walk you guys through how the sticks and stones strategy works. So we have these 10 pieces of purple triangle candy. So, and we've got our 4 friends, yay. And so we can try to assign the candy by grouping them together into 4 groups like this. So the little blue guy gets like 2 pieces of candy. The orange guy gets 4 pieces of candy. The green guy gets 3 pieces, and the brown guy gets 1. And so, yeah, that's one way to group the candy and organize it. But a better way would be, instead of using circles to group the candies, we can instead use lines to divide them up based on the position of we can just draw lines where the circles sort of like meet, So this divides up the candy using only 3 things, which I'm just going to call sticks from now on, because that's basically what they are. We're using 3 sticks to divide the candy into 4 groups, where the leftmost group belongs to the blue guy, the second to leftmost group belongs to the orange guy, the second to rightmost group belongs to the green guy, and the rightmost group belongs to the brown guy. So why are we using these sticks instead of circles to group the candy? Well, because with these sticks, we can really easily adjust who gets how much candy. So, for example, we can make it so this guy doesn't get any candy. Notice how like the way we assign the groups is just by the order. So the leftmost group will always belong to the blue guy, and then of course the rightmost group will always belong to the brown guy, even though like right now there's nothing in that group. We can even make it so that only the blue guy gets the candy by stacking the sticks on top of each other at one end. So that way the other 3 stick figures are kind of sad. Yeah. The point is though, is that we basically changed the problem into just a matter of how many ways can we arrange 3 sticks and 10 triangles, which I mean is actually a lot easier to solve, because now we can actually use our combination strategy for this. Because in total we have 13 objects, right? And the positions of the 3, because, okay, I'm going to explain it in a different way. We have 13 objects now, right? So using our if we have 10 of one object and 3 of another. So the total number of ways to arrange this would be 13 factorial. And then we divide by 10 factorial because these 10 objects are identical. And then we also divide by 3 factorial because these objects are identical. And wait a second. Okay. So we can just evaluate 13 factorial divided by 10 factorial times 3 factorial, which is 286, I'm pretty sure. So, oops. Yeah. So do you guys see how this is actually pretty useful for like solving problems or distributing objects among like 4 or 5 groups?
It's actually, yeah, it's super useful. It's actually, I actually remember the last question during, I think it was MC8. I actually think it was MC8. The last question had to do with, it might not have been the last question, but one of the final 5 questions was a bus question. Remember, Amy? It was like a
I don't
bus. It had
remember.
to do with, it was a sticks and stones question that had to do with the bus. It wasn't AMCA, like an official MC8 test. I remember taking it.
But we
Why
do
do
13
why do
choose
we
3 because there's 10 candies and we have these 3 sticks which we're going to use to divide the candy. However, we can just consider the sticks as part of the overall group. That would make there be 13 objects. So yeah. And we don't do 10 choose 4 because if we do 10 choose 4, then that means we're basically choosing 4 objects out of 10 objects, when in reality, we're actually dividing up the candy into 4 groups.
I'm a bit confused on what you just said.
Okay, so, okay. So wait, what are you confused about?
Like the 10 choose 4 and like we'd
Okay.
have to take 4 objects out and stuff. Like I was kind of confused on that. Can you please?
Oh, okay. I can re-explain it. Basically, someone just asked why do we do 13 choose 3 instead of 10 choose 3, and why 10 choose 3 instead of 10 choose 4. Basically, we do 13 choose 3 because here we have 13 objects. We have 10 of these candies and 3 of these sticks, which we're going to use to divide the candy into 4 groups. We don't do 10 choose 3 because there are 13 objects, and also we don't do 10 choose 4 because we're using the 3 sticks to divide the candies up into groups. We're not gonna, if you just do 10 choose 4, you would be choosing 4 candies out of 10.
Oh, okay.
Yeah.
Got it. Thanks.
Yeah, 4 choose 10 wouldn't work. The other question, but 13 choose 10 picks 10 things. Why do we need that? Here, I'm gonna rewrite it. 13 over 10 factorial, 3 factorial. We're basically arranging 13 objects, of which 10 of them are the same, are identical, which are these candies, and 3 of them are the same, which are these sticks. If you think about this as like a word, you have basically 10 letters that are repeating, and you also have 3 other letters that are repeating. So when arranging these around, we do 13 factorial divided by 10 factorial divided by 3 factorial. So the answer is 286, yes.
Yeah, so sticks and stones problem, I mean, not the problem, just with the concept of sticks and stones is actually so useful because you get these distribution problems a lot, and no normal combinations of permutations don't give you the answer to this. So yeah, and also remember, if you're trying to divide it among 4 people, you only have 3 sticks, right? Because you have the leftmost and the rightmost group. So you don't use 4 sticks, you only use 3.
Yeah. So for if you have, say, 7 people, you wouldn't use 7 sticks. You would use 6 sticks because you only need 6 sticks to divide it into 7 groups. Okay. Are there other questions? If not, we're going to move on. Okay. Now, I'm going to also introduce a variation of this problem. Same thing, except now, Jordan, still has 10 pieces of candy, still has 4 friends, but this time he wants to give each of his friends at least 1 piece of candy. For this problem, what we do is that we simply take out 4 of the candies and assume that they're already given to his friends. That way, each of his friends already starts off with 1 piece of candy. So they're guaranteed to have at least 1 piece. Then, let me just, oops, I'm sorry, shoot. Okay, whoops. Let's go back down to the slide. Okay. Here we go. All right. Basically, we assume that these 4 candies are already given to their friends, and then we just assume everything else goes as normal. We now, instead of having 10 candies, we have 6 candies left, and we just do everything as normal. There's a total of 9 objects here now. So we do 9 factorial divided by 6 factorial times 3 factorial. That equals 84. So yeah. Are there other questions?
What's the stone part in like sticks and stones?
Oh yeah,
Don't
forgot to
use the
mention.
objects.
Stones
So
would be the
sticks-
candies.
Yeah,
Except
the
like
sticks
candies
are the
is
dividers.
more appealing.
Yeah.
Okay.
The sticks are the dividers. Yeah, we don't want to be violent. We don't promote violence, right? So we replace stones with candy. These candies are sweet.
Yeah.
Stones are
You could do like candies and licorice or something. I don't know. Okay.
Yeah.
Okay. You guys can try to do an example. Walter needs to sort 16 identical jars into 3 different boxes. If each box needs at least 1 jar in it, how many ways can Walter sort the jars?
Yeah, you guys.
If you're confused, you can always draw a picture because pictures are great.
Yeah, they are. Pictures are very efficient. You guys should read the problem very carefully. Oh, so it looks like we're getting okay. Yeah, 1,680 is a little far off. $48. Nope, not quite. Nope, 78 isn't it either, guys. I'll explain it. Looks like we're struggling with this one. Okay, think about it. Each box has to have at least 1 jar, so that leaves us with 13 jars left. 13 jars into 3 different boxes. So remember what I told you. Since we have 3 different boxes, instead of 3 sticks, we use 2 sticks, right? Because we can divide the stones into 3 different groups with only 2 sticks. So we have 13 stones or 13 jars and 2 sticks. So that gives us a total of 15 different objects. So we have to choose 2 of these objects to be our sticks. So just 15 choose 2 or 105. So I think we have to try one more. I think we should probably try one more. Amy.
Um,
Yeah, we'll try one more here.
Right.
Let's just try
Here.
one more. Okay.
here,
I have here. I'll just put it in chat actually.
Oh, 13? 13 is because, okay, I can re-explain this problem. So we have 16 identical jars, right? And I'm just going to go back a little bit. 16 identical jars. I drew the jars as these red circles, okay? So we have these 16 jars. Then we have 3 different boxes. Remember that, and that means we're dividing the jars into 3 groups. remember that in order to divide something into 3 groups, you actually only need 2 sticks because the spaces around the sticks are the groups. So here are our 2 sticks, which are in blue. And over here are our jars, which are in red. Now, the question does say that each box needs at least 1 jar in it. And since each box needs 1 jar in it, that means we can just assume 3 jars are already placed in the boxes. That way, each box is guaranteed to have at least 1 object. So now what we're left with is 15 objects, 13 jars, and 2 sticks. So then we just need to find the total number of arrangements of these objects. And that number of arrangements is the number of ways we can sort these 16 jars into 3 boxes. So we would do 15 factorial because there are 15 objects over here, divided by 13 factorial times 2 factorial. We do the 13 factorial times 2 factorial because there are 13 jars here. And if you think of them as letters, they are repeating letters. So you need to divide by 13 factorial. And then we divide by 2 factorial because of these 2. So that would be 15 choose 2, which is 105.
Okay, I put a new problem in chat and I want you guys to try and solve it. And I won't say if anybody's right or wrong yet until we get answers. I'm gonna call on someone to explain their answer. Okay, so looks like we have a few answers. Vishwa, can you explain how you did this problem?
Yeah, so 13 oranges. And then if you want 2 oranges for each of your 3 friends, then that's 6 oranges. That's gonna go anyway. So then so right now you have 7 oranges. And then you need 2 lines for the 3 friends. So that's 9 total objects times 7 divided by 7 factorial for the oranges and 2 factorial for the lines.
Okay, so it's 9 factorial, or it's basically just 9 choose 2. So we get 8 times 9 divided by 2, which is 36. Yep, that's it. The answer is 36. Good job, guys.
Wow.
Why would we only have 2 sticks though?
Okay,
Remember
so
sorry.
actually,
You
Amy,
can.
no, Amy, actually demonstrate because you have a diagram already up. So go ahead and demonstrate that.
All right, I'm gonna clear this. So basically, if we have a bunch of objects, right, and we want to divide them into like 3 groups, 1, 2, 3, notice that there's only 2 boundaries between the groups. And what the sticks are representing are the boundaries between the groups. So even though there's 3 groups here, there are only 2 boundaries needed to define those groups.
Oh, okay. I thought they would need 3 sticks because of the 3 groups.
Yeah, only 2 are actually needed.
Thanks.
Okay. Clear? No questions?
Yeah.
Okay. Okay, I'm just going to quickly summarize this. If I want to sort m objects into n groups, what we do is we take, oh shoot, okay, hold on. There we go. Okay, so we do n plus n minus 1 choose n minus 1. That sounds like a bunch of random letters and some random numbers. So I personally don't prefer this formula. I just like thinking about it in my head. So yeah, I think you guys would probably better thinking about it in your head and working out, okay, how many stones would there be? How many divider sticks would there be? And then you find how many ways you can arrange them.
Yeah, you probably shouldn't memorize formulas. Always try to avoid memorizing formulas unless like absolutely necessary. Like the quadratic formula, you're gonna need to memorize that formula. But these formulas, you can just understand and do the problem. You don't really need to memorize these. These are just like for the sake of generalizing these problems. You probably most likely do not want to memorize these.
Yeah, just rather think about it in your head and work it out. So yeah.
Yeah, don't try to memorize.
I'm not going to go to the Jamboard quite yet because we have some very fun line problems.
Yes, so line problems are my favorite counting, well, one of my favorite counting and probability problems because they're actually pretty fun. They're actually pretty fun.
Yeah.
So how many paths are there from point A to point B if you can only move right or down? And the way, like when I first found out the way you do this problem, I was like really shocked because it's so smart.
Yeah,
It's
I
so
kind of was
cool.
like mind blown. I was like, what?
It's pretty cool, yeah.
Yeah, so I can just quickly show you the basis for this strategy. Basically, for no matter what path you take from A to B, I'm gonna trace out the path because it helps to see. I'm gonna trace out a random path. No matter what path you take, there will always be 4 paths to the right and 3 paths down. Always. Like in every possible combination of line paths, we'll have 4 paths to the right and 3 paths down. Like if you really want convincing, just like spend some time tracing it out and see why. But this is like really useful because we can basically then write out every combination of paths as a sequence of moves where let's just use the letter R as right and D as down. So that means in order to get from A to B, we just need 4 R's in our sequence of letters and 3 D's in our sequence of letters. So we could have a path that is R, R, D, D, R, R, D. That would be right, right, down, down, right, right, down. So in fact, since every sequence from A to B consists of 4 rights and 3 downs, our problem has now suddenly become a matter of finding the total number of ways to arrange these letters, 4 R's and 3 D's.
Well, yeah, I think you guys can do the rest, right? Like how do you arrange 4 R's and 3 D's? You guys know how to do this. We've been over this so many times. So everybody here, I think, should be able to do this.
Remember, there's repeated letters.
Remember, they're basically just repeated letters. How do you arrange 4 R's and 3 D's? Remember, R represents right, 3 represents down, and all paths, no matter the path, no matter like the direction, no matter like the order, all paths are gonna have 4 R's and 3 D's except different combinations of these 4 R's and 3 D's. It's 35, guys. So yeah, I expected you guys to know this. But yeah, so there's 7 total letters, right? And then we just divide by the repetition. So 4 factorial and 3 factorial, which gives us 5 times 6 times 7 divided by 6, which is 35. So yeah, let's kind of, why don't we go and try a different problem to see.
Oops. Okay, let's do this one. All right, this time we're going for finding how many paths are there from A to B that only move up or right. So again, think about it. What does each path consist of? And then you can denote those by letters, and then you can make arrangements.
$21. All right, good job, guys. Good job. Okay, so that is indeed a good job, right? So look, I'm gonna ask someone to explain it actually. Let's see. Sahil, do you want to try to explain this?
So it would be like, since there's 5 to the right and 2 down, it would be 7 factorial over 5 factorial and 2 factorial.
I just want to start. It's 2 up, I think, right?
Yeah, 2 up.
2 up, right? 2 up. Sorry, and then it would be equal to 21.
Yeah.
Nice, nice job, nice job. That's exactly how we do this problem. That's a nice job. Good job. Okay, but now we're gonna transition into some weirder grids. And the same strategy doesn't necessarily work for these weirder grids, but we have a different strategy for them.
Yeah.
So the strategy for finding this grid out is the first thing that you do is find the origin point, which is A, right? And you label everything on the border, like directly on the up and right of the border as 1, because there's only one way to get to it. So actually, I think it's actually on the next slide. The way that we do it.
It's here. Sorry, I just put a bunch of transitions.
Okay,
Basically,
my
what
bad.
this strategy does is that it counts how many paths there are to the vertice that you're on. So for example, how many ways are there to get to point A? Well, you're already on point A, so there's only one way to get there. But then, like, for example, this vertex right here, or vertex right here, this only has one way to get to it also, or sorry, up here. Point is, all these vertices on the side and up here only have one way to get to it because you must just continuously go right or continuously go up to get there. Oops. What you do next is pretty cool. If we take this vertex right here, we have to give it a number. And what we do to get that number is we add the values of the vertex to the left and below. Because why do we add the vertex from the left and below is because we're moving up and to the right. And these numbers represent how many paths there are to this vertex. And since there's from these paths, there's only one way to get to this next one, so we add them up. So this value would be 2 because we do 1 plus 1. And this vertex would have a value of 1 plus 2, which is 3. This vertex here would have a value of 2 plus 1, which is 3. This vertex here would have a value of 4 plus 1. This vertex here would have a value of 4 plus 1, which is 5. And then up here, this vertex would have a value of 3 plus 3, which is 6. This vertex here would be 6 plus 4, which is 10. And basically, we just keep doing this all the way until the end. So over here, it would be 10 because there is no connecting line down here. So this would just be 10. And then up here, this would just be 6 because there's nothing here. And this one would be 6 plus 10, which is 16. And finally, at the end, this would be 16 plus 10, which is 26. What this number means is that there are 26 paths that only move up and down that go from A to B.
And it's actually such a cool problem.
Yeah.
It's very nice. It's a very cool problem.
Yeah, I mean.
How'd you do that? Okay, so okay. Yeah.
Hold on. Let me ask. Are you confused at how we did it, or are you confused at why it works?
Both. First, I would like to know how you did it.
Okay, I'll go back. When we first start off, we have like our starting point A and our end point B. And our starting point A will have a value of 1. Remember that these numbers represent how many paths there are to this point. Since we're already at point A and we can only move up and right, there's only one way to get to A. And what we do is then we mark all the vertices here, and here. In other words, all the vertices that are directly above and directly to the right of A, we give them also all 1s. So, the reason we give them all 1s is because there's also only one path to get to them. To get to any of these vertices, you just have to keep going to the right, and there's no other alternate route. So these vertices all have values of 1. But then to get subsequent vertices, what you do is, so for example, let's look at this vertex right here. What we do is that we look at the value that is to the left and below, and then we add them up. So this vertex would have a value of 2 because 1 plus 1 is 2. We couldn't go up.
So you actually can't go down. You can only go up and to the right. That's the problem states. You can only go up and to the right. You can't move left or down. So you don't count any of those. You don't consider any of those.
Because if you think about it, there's no way you can take you can't take a path where it goes up, right, and then back down to a vertex. So there's essentially 0 paths that go from a down. So yeah. So again, the premise here is that every vertex is going to be the sum of the vertexes that flow into it, if you think about it like that. So this one here, this one would have a value of 3 because this vertex has a value of 1 and this vertex has a value of 2. So this vertex would have so that means 1 plus 2 is 3. So this one here would have a value of 3. And basically,
weird
The reason why it works is because if you think about it like this, there's one path to get to. First, let's just agree that there's one path to get to this vertex, okay? Because we can't do anything else fancy like that. We just have to go straight to that vertex. So there's only one path there. This vertex here, there are actually two paths. We can go from here, so we can go up, right. We can also go right, up. So there are two paths here and one path here. So then
another thing that I want to mention is that think of it like this. The only way we can get to the point that Amy's thing, what is that, a pen? Yeah, the only way we can get to that point right there is through the green circles. So those green circles points are the only ways that we can get to that point, right? Like by moving up and right. So by considering the total ways we even get to those paths, and like we can just add those up to get to how we can get to the 3. So think about it like this. There are only 2 pathways we can get to the 3. There's only 2 pathways, okay? So we know that there are only those 2 paths. We can count. So by counting the total number of ways we get to that path before that, right? And then by adding both of those up, we get the total number of ways we get to that certain path. And that might sound really confusing to you guys, but like you'll start to understand it as you kind of do it on your own. And it's something that I encourage you to piece together by yourself.
Yeah, you could also just do this. You can see that here's a path to this 2, and it takes one more step to get to 3. So that's one path. You can go also here, and that's all the paths that pass through 2, but also go to 3. It's 2 paths. And then we can also see the paths that go through this point. There's only one path that does. And from then you just go to 3, which is one path. So I know it sounds kind of weird, but yes, it's fine to be adding them up. So yeah, you basically just do this across the entire grid. And once you reach the end point, you have your answer, which is 26.
Fun.
All right.
Okay, we can move back to the slideshow.
All right, wait, I hope I don't have anything else after this. Okay, no, we don't, except the Kahoot, which I hope we can
what
get
we're
to.
gonna do, I think what we can do is just skip to slide 12. Let's skip to slide 12, Amy.
All right, okay. All right. How many paths are there from point A to point B? And if you guys want to like write on the Jamboard and start numbering, you can definitely do that. Yeah, 1, 1, that's right. Yeah, so far so good.
Okay. Whoa.
Okay, pause right there, guys. Pause right there. I think okay, I'm gonna erase some of your things.
Yeah,
Just don't erase anything else. Don't erase anything else. No, don't be erasing those. Okay, this 6 was right. Oops.
Okay, but wait, I already put it. Wait,
Yeah,
okay, so that's right. The thing is, you see this point right here. That point has no other way of being that point cannot be reached by any other way except through this point right here. So what we do is make this a 3. That's also a 3, and that means that this becomes a 9. That becomes a 9. That does not look like a 9. Amy, you can write the 9.
Also, the point in this little point right here in the upper corner, this would also have a value of 6.
6. 15,
Which
27.
ways
You guys got
can
it
we
right.
move?
Write it down. Sorry if I
Okay.
didn't specify that.
Wait, you guys did it though. Like, good job. Wow, that was so fast.
Yeah, that
you
was
guys did
fast.
it so fast. Wow, okay. Well, we can just move on to the next problem.
Okay, this one is a little bit different, but use the same strategy. How many paths are there from point A to point B if you could only move right? Like, for example, you can move this way and you can move this way.
Yeah, this is how I considered it. I didn't really have a name for these directions. So I just did this.
Upper right and upper down.
and I call these A, I mean X and Y, movement X and movement Y, like kind of like vectors. So
Careful, 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 guys. Okay, you guys have to be a little bit careful when after you cross this middle point, you can't keep numbering ones anymore, because if you notice, this point can take both this point and this point.
wait, another thing that I would suggest is probably don't use this one strategy. And like I think I would only use this for like grids that are damaged. Like number 12, there's some holes in the grid, obviously.
Yeah.
But for this one, there's no holes in the grid. So it'd be way more efficient. Actually, no, you guys, I actually encourage you guys to still try the strategy to see like how they
it's
line
fine.
up. No, just to completely out. Actually, I actually encourage you guys to still continue trying your strategy. Yeah.
Yeah.
Nice. Nice. This 4, okay, that's 10.
No.
This I'm gonna help you guys out a little. So this is 4. This is 10. And now we get is ready for this 20. Nice. Now we're
Yay.
gonna try. Now we're gonna try it the other way. Three x's and 3 y's. 6 factorial over 3 factorial, 3 factorial. Let's see if we get the same answer. 4 times 5.
Yeah, that's 20. 3G's or 6G's 3
times 6, and we get the exact same answer. So that's nice. Good job, guys. You get the exact same answer. Both ways we use, we get the exact same answer. And this demonstrates our proficiency in utilizing these methods in order to efficiently solve these line path problems. So good job, all right? So it looks like you guys correctly understand how to solve this problem, which I'm pretty happy about. So yeah, very, very nice job.
Yep.
Now we're going to do 14, which is not a line path problem.
No, let's
Do
not
you
do
wanna
14. In fact, let's go back to one of the sticks and stone problems.
Yeah, let's go back to one of those then.
Let's go to slide 10, sock problem.
Okay.
Slide number 10.
Weren't we gonna do slide number 2? Like
Oh yeah, we
someone had a
can.
question.
Oh yeah, we can do that after we finish the sock problem.
Okay.
All right, we're on this problem, which says, how many ways are there to sort 8 identical socks into 3 bins if each bin needs at least 1 sock? Also, you can move around these socks, but I don't know what the point in that is, because you don't really need to move around the socks. Oh, someone has the answer. Okay, each bin needs 1
21.
sock. Yeah. Yeah, 21 is the
Because-
correct answer. How did you, or we should probably call on someone to explain.
Okay, Vishwas, it looks like you already circled the answers, so just tell us.
So 8 socks, and then each one needs 3, so you can start with 5 socks now. And then you have 2 lines for the 3 bins, so 7 total. And then 7 factorial over 2 factorial for the lines and 5 factorial for the other socks.
Yeah.
You're right. Good
Nice.
job. Okay, so it looks like a lot of you guys are getting the right answer, which is something that's, it's cool to see. You guys understanding the concept. That is nice. We can move to we'll do number 9 now. Let's just move back. It's an easier version of the problem we just did, like, to be
Yeah.
honest.
Wait, Sai, do you want to like do the Kahoot or something?
Yeah, actually, we have time for the Kahoot. Let's
Yeah,
do the Kahoot.
finally.
Yeah, we have time for the Kahoot, guys.
Okay, we might need to hurry though.
Yeah, we might have to. No, it's fine. We still have time for the Kahoot.
Could you wait for 1 minute? Like, don't start yet. I have to leave and come back for a second.
All right, sure. Here's the code.
so
Also,
exciting.
while we're doing it, while people are joining the Kahoot, we can go over the slide 2.
Is it mandatory to play?
Oh no, you don't have to play, but I mean, we encourage it.
Guys, we do encourage it. We haven't had time for a Kahoot.
Yeah,
the
we had
past 2
Kahoots
lessons.
planned.
Is it
No,
for
it's not
grade?
for a grade. No, it's just for fun.
It's a show like for concepts. Come on, guys.
Also-
I encourage you guys to join.
Yeah,
But can you go back to the game pin, Amy?
I already put it in the chat.
I'm not gonna join though. You know what I mean?
You should. Or I don't know.
I'm not gonna join. I'm not gonna join, guys.
Yeah, he's definitely not gonna join. He's
I
definitely
actually,
not gonna call himself not Psy.
Can we use funny names?
Yeah, you can definitely do that. I mean, you can basically use any name as long as it's not like inappropriate. Wait, guys, can you hear the music or no?
no, it's fine.
Oh, okay.
Nuclear.
Your volume is really low on that, like on the Kahoot, so we can't hear it.
You guys have pretty nice names. Amy, I think you have to have audio optimization on Zoom.
All right, that's fine. I don't need it. Okay.
Music.
You know,
Okay.
I'm gonna just
Could you
start
wait
now.
for 1 second? I'm about to join.
Yeah.
Okay.
Yeah. No problem.
There's barely anyone there. Hi, and I see.
Okay, just tell me once you're in. Oh, okay. Okay, yeah, I guess you're in. All right, we're gonna start now. You can still join if you want to later. All right. Okay, 12 people at a party. Each person shakes hands with every other person. How many handshakes occur?
Wow, you guys are doing this pretty fast.
Okay. Yeah, the answer is 66.
We can go over it later.
Yeah, we're just gonna have to go fast. Okay, 10 teams in a tournament. Each team plays their other team twice. How many matches occur? Also, I might be ending some of the problems early because we might not have enough time to finish. Okay, 10 teams in a tournament. This time, teams are playing each other twice. So you would not need to actually divide by 2. Oh, nice. Oh, wow, Sai, you're not.
That's not me. I don't know what you're talking about.
9
It's actually
identical
not.
gloves,
I don't
3
know who that is.
pins.
I might have got this wrong.
It would be funny if you did.
That would be sad actually.
Yeah.
Now we have evidence that Psy is playing.
Yeah.
No, I'm just joking. I meant like I'm joking. No, I'm not playing. I don't want to ruin your guys' fun.
Okay, yeah, 9
Wait.
identical. Did you get it right or wrong?
I got it wrong.
Definitely.
Oh, wow.
Oh
Okay,
Now
my
we
God.
definitely have evidence size in the game.
Whoa, look, Amy, I think you might have. I think the
Did I
problem
mess
might
up?
have been. Yeah, you
Did I
messed
mess
up on the
up?
problem. Yeah, you messed up on the problem.
Okay, whoops then.
Because it's 9 and 3, right? So that'd be 11 choose 2, which is 66.
No,
Oh,
it's
it's
55.
55.
I did the calculation.
Okay. We're gonna move on. We're not gonna talk about what just
Yes,
happened.
you're smarter than Psy.
Oh my God. Oh. Oh,
Okay, yeah. This time it's at least 1 glove, so yeah.
50% accuracy.
Okay.
Hi.
Tragic.
Wait, I can't see through the chat. Okay, I'm hoping green is okay.
That is
I'm gonna
definitely in the game.
give me the answer on accident. Maybe.
Oh, yay. A lot of you guys got it this time.
I said green. I said green is the right answer on accident.
Okay. And you could put 6 different beads on a bracelet. How many bead arrangements are there?
This is easy. I expect. Oh my god, I got this one wrong too. Wow, I'm having a really bad day.
I got this wrong too.
I
Uh-oh.
forgot the flips. You forgot there. I think a lot of people might have forgotten the flips. You have to add in the flips on rotations. Yeah, it's actually blue, guys.
Oh.
Blue. It's
Yeah.
blue. It's blue.
Hmm.
Oh wow. Oh my god.
How many paths are there from A to B if you could only move down and right? This is not too hard, I hope.
Yeah, it's not hard. Everybody should be getting this one.
I forgot about how to do this, so I kind of guessed.
Oh,
Okay, remember, 2 down and 3 right? So
Yeah,
it's
I
5.
also forgot.
uh-oh.
Okay, we'll go over it later we'll go over it later, guys.
All right, I could just do it quickly. There's 2 down, 3 right. So if you think of them as letters, the 5-letter word with 2 repeated and 3 repeating. So you do 5 factorial divided by 2 factorial divided by 3 factorial. Ugh.
Oh.
Okay, so another one.
Okay, this is the weird one. What?
You
How
may
do we-
want to draw it on your paper, or maybe you don't have to
No,
if you think
I-
that this number.
I'm gonna get this one wrong too, Amy.
Okay, yeah, that might have, yeah, for that one, you would just have to number it. So you would number 1, 1, 1, 1, and then 1. And then from then you just add them. Can't really explain right now because we're basically over time. Oh, wow. Okay. I know since class is technically supposed to be over, you guys can leave if you want. But if you are a fan of Kahoot and you want to just keep playing, you can.
Why do we get these problems? What?
Okay, that
Okay.
might be hard to draw, sorry.
Yeah, this will be.
You're
not
gonna see a
easy.
similar one on your homework, let's just say.
Yay.
Yeah, we love homework.
Also, why are there 50 seconds on this one?
Yeah, we should be a
because
little
it'll
bit
take,
time.
I don't know.
Because it takes longer.
It
Yeah,
does take.
the only,
Sure.
okay, yeah, maybe I should have added more time.
It's fine. It's fine, Amy. If I embarrass myself, it's because of you. Yeah, this is not gonna. This is not gonna end well for me.
These are hard. At
Yeah.
least on homework, we'll be able to practice.
Oh,
Oh,
wow,
yeah.
only one person got it right.
Who got it right?
Vishwa, wow, nice. You're fast. I don't know, maybe you're, I mean, are you drawing the diagram? Wow, okay. All right, 3 coins are flipped, one after another. How many different combinations of heads and tails are possible? This one's a little bit easier. Don't overthink it. Oh, wow, fast. Okay, yep, the answer is 8 because it's just 2 times 2 times 2.
Okay.
Calculate 5, choose 4. I don't know, I kind of got lazy with the questions back here.
Yeah, maybe. I'm gonna get this one too. I hope not. No, I think everybody should get this right. I think this is the easiest question.
Yeah, this is fairly easy.
Yeah. Okay. Yep. 3-letter sequences don't have the letter Z. Okay, that is a little bit hard. Wait, is it hard? No, it's not hard. Never mind.
It's not that hard.
I actually was a little bit confused at first, and then I was
think you
like,
should just have to put some logic into it. I actually got it.
yeah, you just have to
Well,
think
could I
about it.
see how to do it after this?
It's yeah, we could at the very end. It's actually quite very easy. It is an easy problem.
3 letters, there's only 25 choices for each letter since normally there'd be
And then
26 choices.
It's 25 cubed, yeah.
Yeah.
How many 3-digit sequences have 2 digits? Something? Yes, Amy.
Yeah.
Yes. What are you? Okay. This is an easy problem.
Yeah, this is not too hard because there's only one. Okay, have 2 digits sum to 18. The only way you could have 2 digits sum to 18 is if they're both 9.
Well, thanks for giving the answer.
There's still another thing you have to consider, which I'm not going to say. Or if you want me to say it, I can.
Yeah, I'm going to get this wrong because of you. Gosh. You know what? I probably am going to get this wrong. You know what? It's fine. I've already lost the battle.
I
Oh,
feel like I got this wrong.
Oh, must you got it right. Sai, did you get it right?
I got it right. Okay, that's nice.
Okay, yeah. Basically, 2 of the digits have to be 9. So, but however, sometimes if you have 999, you don't want to like accidentally overcount it. So yeah. Calculate. Oh yeah, I got lazy with this one too. This one's actually really easy. You don't even need to use a distributive property for this.
It is quite easy.
Also, if some of you guys need to leave, you can definitely do that because we're overtime by like 5 minutes. So yeah. But if you want to stay, that's fine. I appreciate it. Yeah, 6 because 4 back 4. It's really easy. You just split up the little fraction thingy.
Yeah, I used the distributive property kind of, and it really helped.
Yeah. 4 flips a coin. How many ways are there to flip at least one head? Complementary counting. Hint, hint, hint.
Yeah, this is an easy problem.
There's at least 7 ways. That's the answer.
Uh-oh.
No, it's 15, right?
Yeah, it's 15.
It's okay. No, who is this winner AR? Who is winner AR?
I mean, it's pretty accurate. Yeah, it's Advika. Yeah, I kind of.
Okay. You know, this one's easy as well. So, well, it's not. I think we learned about it. So,
actually, we did. Okay, we did something similar to that in the homework.
Yeah.
Dan, I think you did some sort of line problem on that too. I think.
Oh yeah. Yay, 28. It's actually just 8 choose 2.
I just wanna be first. It's not that hard to ask.
9 points spaced. Find the number of distinct triangles this time. I don't know why I included by connecting 3 points because that basically just gave it away. Or actually, I don't know.
Probably got this wrong actually. Now that I think about it. Well, actually, I think I got it right. There might be a twist, right?
I don't think this one has any twist. It's just,
if it doesn't have a twist, then I got it right. Yeah, then I get it right.
I don't think it should have a twist because it's spaced along a circle. So there shouldn't be any weird overlapping things. Yeah, it's 84 because it's just 9 choose 3. Nothing out of the ordinary for this.
I need winner AR to get something wrong.
Oh no, I did this wrong. Oh my gosh. Wait a second. Oh wait, no, I didn't. Okay, never mind. I thought, okay, never mind, guys. False panic attack.
False panic attack.
I thought for a second that the lines could be crossing each other. But then I was like, then I realized that that wouldn't happen because we're just choosing 4 points and there's only one possible
Yeah, we're just,
quadrilateral.
yeah. The order would, it doesn't matter the 4
Yeah.
points. That would just depend on the order. Yeah, you're right.
Yeah, but
It-
like
the-
we're doing combinations, so the order doesn't matter.
The lines would not cross each other.
Okay, 210. 10, choose 4.
Nice. Okay, I hope the person that got it wrong does not win.
No.
Nice.
Oh man.
Oh.
All right, GG's guys. It was really fun.
Oh wow. Fast. Okay. Let's see the leaderboard.
Ah, I wonder who won.
Okay, good job, Nuclear Pat Stuff 47. Good job, winner AR Aditha. And of course.
I have no idea who this is.
Wait, how did you get 15 out of 19, Sai?
There were some questions which I should not have gotten wrong, but I none.
Oh wow. Oh wow, good job, Strayan.
So close.
It was the line questions. I did so bad on those. Okay,
Wow.
I don't. It's okay. It's okay. I'm actually pretty bad with those, but they're still fun nonetheless.